Okay, so it is 12, so let me start. Yeah, any questions by the way? So I'll be taking the classes for the rest of the semester, about 1 month. Yeah, so please don't mute me. Someone had muted me, maybe accidentally. Okay, so as I was saying, yeah, I'll be taking the classes for the rest of the semester. So what we are going to do is this week, yeah, we will revise a little bit of Fourier transforms, continuous and discrete, and from next week we will start with Laplace transform. So yeah, the understanding of Fourier transform will be crucial if you want to study Laplace transform. So we will just revise a few things and sort of connect discrete time and continuous time Fourier transforms, how they are related to each other. And yeah, once we have a proper understanding of Fourier transform, that will help us in understanding Laplace transforms also. Okay, so this week will be sort of a revision. You can also treat it as a tutorial. We will go through some properties and look at some examples. And we will also, if time permits, we will also look at discrete Fourier transform. So that is DFT. So FFT algorithm basically. It's not part of the syllabus, but I thought maybe we should have a quick look at that because we are anyway studying discrete time Fourier transform. So yeah, why not have a look at FFT also? So that we will probably cover on Friday, and we'll discuss some problems also on Friday. And yeah, next week will be Laplace transform followed by Z transform later on. So that is 3 weeks starting from today. In the fourth week, we will look at sampling theorem. Okay, so sampling and reconstruction, and some basic filters also, low pass, high pass, band pass filters, and so on. And at the very end, we will look at some linear system properties and things like that. Okay, so that's how we are going to plan the rest of the semester. Uh, so there is no submission or no exams in between. Yeah, the exam will be the NSEM exam. Okay, so there is no intermediate exam, no submissions, but problem sets I have uploaded, so you can have a look and uh, try solving some of these problems. I will also discuss some of them. All of the problems, yeah, I won't be able to discuss. But I encourage you guys to discuss among yourselves, and yeah, offline, yeah, we can discuss also. So if required, yeah, let us see if everyone agrees, then we may have extra class or something on weekends to discuss problems if you want. Okay, I'm not going to impose it or make it mandatory, but yes, if enough people are interested, then yeah, we can have one or two extra class if required. Uh, okay, so notes also I have uploaded, so yeah, you can have a look at them also. So PKD sir's notes, my notes, along with Oppenheim's books. So this is basically the reference. Just one of these, yeah, may not be enough, yeah, for understanding everything. So it's better that you look at all of these things. Okay. So just attending classes, yeah, that will not be enough to do this course properly. So class along with yeah, notes and the reference book, okay, and problem sets, things like that. So any questions or comments before we start today's class? Let me share my screen. Okay. So hope my screen is visible. I'm using Windows machine because my Linux machine has some speaker issues. I've not used Windows for a long time, but hopefully that should not be a problem. Okay, so, all right. So I hope this is visible to all of you.
Yes, sir.
Yeah. Okay, so if there is any question, feel free to ask questions. Okay, I will also keep checking chat box, but yeah, I'm not sure if there are too many questions in the chat box. Then yeah, since this is a very big class, I may not be able to address all of them. But yeah, you can also help each other and yeah, resolve each other's questions in the chat box. And yeah, if you feel like interrupting with some question, yeah, don't hesitate. Okay. But yeah, don't unmute unnecessarily. That noise otherwise is disturbing. Okay, so let me start. Okay, so as I said, we are going to revise a little bit. So yeah, let me share some alternate viewpoint on this transform. So yeah, you have already had a look at these things. So yeah, this is just some alternate viewpoint I'm looking at. So just giving a big picture, basically, what we are doing when we take these transforms and what really is going on. So yeah. All right. So I hope everyone has had a basic linear algebra course. Okay. So hopefully you guys know what is a basis, what are vector spaces, linear maps, and so on. Okay, so yeah, these first two pages are basically just connecting Fourier analysis, both Fourier series and Fourier transforms to linear algebraic terms. Okay, yeah, just to see things in linear algebraic perspective. So yeah, so let's recall this. Okay, let's consider a finite dimensional vector space. So Rn, this is a n-dimensional real vector space. And hopefully all of you know that this is one of the bases for this vector space. So E1, E2 up to En. So EI basically is 1 at the ith position and 0 everywhere else. Okay. So this is a basis because if you are given any, first of all, this is linearly independent. And if you are given any vector in Rn, you can write this uniquely in terms of these basis vectors. Okay, so x1 up to xn are components of this vector, and yeah, even up to en are this. These are called standard basis vectors with 1 at the ith position. And if you have a standard inner product also, so yeah, inner product of two standard inner product of two vectors, real vectors is x transpose y. So with respect to that inner product, this is an orthogonal basis. Okay. So this is one example of an orthogonal basis in finite dimensional vector space. Okay. Because you have yeah, finitely many indices basically. So yeah, your index set is finite 1 to n. Yeah, each vector you can represent as a unique linear combination of finite vectors. So yeah, taking this perspective a little ahead, let's consider function spaces. Okay, so first of all, we can have this infinite vector. So let me write this. So let's consider an infinite sequence. So starting from x0. Yeah, this is bad. Okay. Yeah, this is a bit problematic, but anyway. Yeah, so this is a infinite sequence of entries. Okay, starting from 0, both forward and in reverse direction. So this entry is x of -1, x of -2, like that, going up to infinity. So this is one example of an infinite dimensional vector space where you have infinitely many entries. Okay, so here we had a finite index set 1 to n. Instead, here we have an infinite index set. Okay, so our index set here is set of all integers set. Okay, so you can have again these basis vectors for this ei. Okay, so I can take negative values now. E minus 1 will have 1 in the this minus 1th position and 0 everywhere else, like that. Okay, so this is a basis for this infinite dimensional vector space. So the index set is discrete in this case. Okay, so again, taking that idea a little forward, we can have a continuum index set. So we can have functions over real line. So index set is real line now, which is continuum. And this is another example of an infinite dimensional vector space. So basis vectors here will be these impulses, Dirac delta functions, shifted train of impulses. So Dirac delta at the origin, then Dirac delta at each real number, and this continuous function you can represent in terms of this continuum of Dirac delta and its shifts. Yeah. So this is an analog of this finite dimensional representation. Okay. So Dirac delta and its shifts, they give another. They give just one basis for this function space. Okay, and inner product also. Yeah.
What is that function space?
Okay, so it is a set. First of all, that set consists of all functions from R to R. Okay, so let me write that. So f is a function from R to R. Okay, so this is your set. Now, if you take any two elements, you can add them, and again, you can check that that element belongs to this set. You can multiply it with any real number, and the element is still a function from R to R. So it satisfies all axioms of a vector space. So that's why if you take a set of all continuous functions, that forms a vector space. Okay, so the dimension of that vector space is infinite, is what I'm saying. Sorry?
The basis, how is it just delta functions?
Okay, so the justification, yes, I'm not proving it is just a delta functions, but yeah, so just a second. So if you, so pictorially, let me show it like that. If I take any continuous function like this, then this function, I'm saying that I can represent it by, so
okay,
I'm going to
sorry, the convolution thing. Okay, yes, it's fine. Yes.
So continuum shift of these train of impulses. Yeah. So that's the big idea. And you can show the independence of these functions also. Okay, so one cannot be written as a linear combination of the rest, and they satisfy this orthogonality property also. So if your two impulses are distinct, then if you take so inner product here is replaced by integration. So let me write that also. So in function space, sorry, your standard inner product, instead of that finite summation, you have integration. And if x and y are your two functions, then it's xy times dt, and you integrate it from minus infinity to plus infinity. Okay, so if you replace these by two Dirac delta functions, which are distinct, then this inner product will be 0. Okay, so that's why they are orthogonal. Okay, so this is this Dirac delta basis is just one basis. Okay, for this infinite dimensional function space. Another basis is complex exponentials, like that. Okay, so you can verify that if you take two distinct complex exponentials, again with respect to this inner product, yeah, if they are distinct, then you are going to get 0. Okay. So this forms another basis. So yeah, with respect to delta basis, what are your coefficient elements? Okay, so that is just function value at each point. Okay, so like we saw here. So value of the function at this point times this delta function. Value of function at this point times yeah, this delta function, and so on. So the coefficient vector will be just the function evaluated at these points. And how you get those coefficients? So in finite dimensional vector space, you just take inner product of with EI. Okay, so EI, if you do that coefficient of x with respect to this basis. So we are going to do a similar thing here. So instead of EI, we are going to get Dirac delta, and yeah, that is just x evaluated at Dirac delta. And if you go to the Fourier basis now, yeah, we are going to take inner product of x with respect to yeah, this is complex conjugate of Fourier. So if you consider complex inner product spaces, then this x transpose y becomes x conjugate transpose times y. Okay, so that's why this is complex conjugated, and this is the coefficient with respect to this exponential basis. And you can interpret this as writing x as a linear combination of complex exponentials like this, and this is the coefficient. Okay, so this is basically the linear algebraic interpretation of Fourier transform. Okay, one is Dirac. In terms of Dirac delta, you get one representation of your original function. Just evaluate this at each point times Dirac delta, and this is another representation using complex exponentials. Okay. Two different bases, Dirac delta and complex exponential, which sort of form the two extremes. So if you represent Dirac delta in frequency domain, you get constants because yeah, you must have seen that Fourier transform of Dirac delta is a constant, and vice versa. Fourier transform of a constant is Dirac delta. So this is that uncertainty principle I am talking about. Uncertainty principle under the rug. Okay. So if you try to localize in one domain, yeah, you get complete uncertainty in another domain. So what do I mean by that is as follows. So if you take Dirac delta, we are localizing exactly at this point, and as a consequence, we don't know anything. I mean, we don't know anything precise in frequency domain because you just get a constant function. Okay. And if you try to localize in frequency domain, then you get complete uncertainty in time domain. Yeah. So this basis in frequency domain, yeah, this is represented by Dirac delta, and in time domain, yeah, you will just get constants associated with those Dirac deltas with some phase factors, of course. Okay. So there are other types of bases also, which we are not going to look at, but yeah, those who are interested, they can explore these things. So they are called wavelets. Okay. But this is not going to be part of this course. So wavelet is basically something like this. Okay, you don't try to localize completely. You take something like this. So this has a finite spread, and Fourier transform of this. Hopefully you have seen this. We will see this today or tomorrow. So this is a sinc function. something like this. So these two form a Fourier pair. Yeah, so neither is localized completely, and yeah, there is some uncertainty, but yes, in some cases you will see that I mean later on if you pursue wavelets and so on, these bases might be better compared to just the delta basis or the exponential basis. Another situation is you can have something like this, so something like Gaussian windows. So they are not localized in either domain, but yeah, you have another Gaussian in frequency domain also. So these two also form a Fourier pair. Okay, so yeah, these can also be taken as a basis, Gaussians and its translates. Okay. Another example for basis is yeah, something like this, which we are going to see in Laplace transforms. Okay. So this S is a complex number now. So recall that for Fourier transform, we just look at the purely imaginary exponent of E. Yeah, e to the power j omega t. So instead of this, we can look at st, where s is a complex number. So you can write s as sigma plus j omega t. Sigma was taken to be 0, okay, in the Fourier transform case, and we are allowing non-zero sigmas now. Okay, so this can be decaying or increasing exponentials, things like that. This does not form an orthogonal set, but this is still a basis. Okay, so this still forms an independent set, but not orthogonal. Okay, so you can take coefficients with respect to this basis, and they will be Laplace transforms. They'll be called Laplace transforms. Okay, so Laplace transforms are basically coefficients with respect to this basis. Okay, so you don't have to understand all this, but yeah, this sort of gives us a connection between all these transforms in terms of linear algebra.
So,
Yeah.
so we are saying they're not orthogonal. Then how can we get a unique transform?
Can you repeat? I could not hear you properly.
So that it's written so that it's not orthogonal. Then how can we get a unique transform?
Orthogonality is not mandatory for unique transform, right? If you have a basis, then your coefficient will always be unique. If your underlying set is linearly independent and if it is a basis, then with respect to any basis, your coefficients are always unique. Okay, orthogonality is not required for unique coefficients. So that's why even though complex exponentials do not form an orthogonal set, Laplace transform coefficients will be unique because they do form a basis.
So orthogonal, so could you repeat the definitions? Like I thought orthogonal meant independent.
Okay, so orthogonal. Okay, so basis basically, yeah, let me go back here. Basis means this, okay, so your set is linearly independent and given any element in your vector space, you can uniquely write this in terms of your basis vector. So that is what is meant by a basis. And orthogonality means your basis vectors are orthogonal with respect to some inner product. So if you take a standard inner product in this case, then EI transpose EJ is 0 if I is not equal to J. So that is what is meant by orthogonality. So this is orthogonality is something which is added on top of basis. Okay, so basis need not be orthogonal always, but yeah, you can choose an orthogonal basis.
Then we call it, if it's not orthogonal, we call it spanning set, right? So like in first year, you're calling it, if it's not independent set of vectors, we call it spanning.
Yeah, but we are still taking independence. Okay, so yes, you are right. If it is not independent, then it is spanning set, but this is independent set. Okay, so that's why this is a basis, not just a spanning set. Complex exponentials form an independent set, but they are not orthogonal. So hope you get that clarified.
Yes, okay,
so if this had this just been a spanning set, that would mean that there is some dependency in that, but that is not true. This is still independent. Is that clear?
okay, so yes.
Yeah. So yeah, spanning would have also made sense, but you would lose uniqueness if it is just a spanning set like you mentioned. Okay, so it is not just a spanning set, it is a basis. That's why uniqueness is there. Yeah, so Laplace transform coefficients will be unique. Oh. Okay.
Sir,
Yes.
we can represent delta function in terms of Fourier transform, right? Then why it is also called in basis? As basis should be linearly independent. We cannot represent another basis in terms of other basis, right?
Yes, yes, you can. So no matter which basis you choose. So yeah, let me go back here. So there is something called change of basis. Right? What's going on?
So orthogonal and independent are two different things, right, sir?
Yes, yes.
Okay, I think that was the confusion. In first year, we discussed them as the same thing.
Okay, no, they are not the same. Okay, so I can give you one example also. Okay, so let me. So this is change of basis. So let me give you one example of a basis which is not orthogonal. So consider R2. So 1 0 and 1 1. So you can check that this forms a basis for R2. Okay, so if I draw it pictorially, this is this vector, and 1 1 will be this vector. So these two are linearly independent, and if you take any vector in this two-dimensional vector space, you can always write this as a linear combination of these two, but they are not orthogonal. And you can check it by taking their inner product also, that they are not orthogonal. So basis does not automatically imply orthogonality, but you can always choose an orthogonal basis. Okay. And yeah, I was talking about this change of basis. So if now I select another basis 1 0 like this and 0 1. Okay, so this vector, so this, let me call this basis v1, this basis element v1, and this is v2. Okay, so with respect to this basis, this vector will be represented as 0 times v1 plus 1 times v2. Okay, so its coefficient will be 0 1 in this basis. Okay, and if this vector, if you represent in this basis, its coefficient will be 1 1. Okay, so if you change the basis, yeah, your coefficients will change with respect to a new basis. Yeah, so there was a question, what happens to Dirac delta? So yeah, for this function spaces, we can choose Dirac delta basis, or we can choose exponential basis. Dirac delta basis, then okay, any multiple of Dirac delta, you can just write that as some multiple of Dirac delta. But if you choose this basis, then yeah, Dirac deltas must be represented as linear combination of these elements. That's what Fourier transform of Dirac delta represents. Okay, so Fourier transform of Dirac delta turns out to be 1 or whatever, 2 pi delta times 1 or something like that. Let's take it to be 1. So what this means is, yeah, you take yeah, something like this, e to the power j omega t. And, so there is 1 over 2 pi factor also, which I'm not writing here. So 1 over 2 pi is there, and all coefficients. So x j omega is 1. So yeah, this is with respect to new basis, our representation. Okay, so just like we saw here, if we change basis, our coefficients change. So in the same spirit, yeah, in time domain, Dirac delta is just a multiple of itself. So yeah, its coefficient is just one non-zero entry followed by all zeros. Whereas in frequency domain, all entries are exactly one. Okay. So I hope that is clear. If this is causing confusion, then yeah, no need to get worried about that. So this is just for connecting all these things. I tried to explain that. So yes, if you find it difficult to grasp or something like that, no worries. You won't be held responsible for understanding these things. But if you do understand these things, then okay, you can see the connection between various transforms. What is going on underneath these things? Okay, so it just helps you connect things basically. It's not mandatory that you have to look at these things from linear algebraic perspective. Okay, so let me start covering some examples and some properties of Fourier transform. So in case there are any questions, there were one or two which we have already addressed. So yes, since we are half an hour past the time, yes, I think we should move on to Fourier transforms now from this linear algebraic perspective. Okay, let's not spend too much time on yeah, just this alternate formulation. So recall these formulas for Fourier transforms and inverse Fourier transform. And yes, so we will derive some properties. Some of them you have already seen, and some of them you may or may have not seen. These are basically exercises. So you can also try this on your own. Okay. I will not do each and every property, but yeah, I will do as many as I can in today's class and on tomorrow's class also. Okay, so one thing we want to understand is taking inverse Fourier transforms from first principles. Okay, so I will explain what I mean by that. So let's start with this example. So the first example in Fourier transform. Once you define what is Fourier transform, so let's take Fourier transform of the complex exponential. The idea is not to show how to get the Fourier transform. The idea is to show that inverse Fourier transform of xj omega is this. Okay, so this is many times not mentioned in standard text. But yes, if you understand this, then we also understand inverse Laplace transform. Okay, so the reason for doing this is yeah, we will just do it once, and yeah, the later manifestations we will just refer to this. Okay, so taking inverse Laplace transform or inverse discrete time Fourier transform, inverse Z transform, you understand all that once you understand this case. Okay, and same for properties of Fourier transforms. So the reason I'm doing this is yeah, this is the most basic case. So treat this as a recursion. Okay, once you understand this base case, you are going to understand everything what is going to follow. So we are going to recurse on this. Just do this properly once, and Laplace transform, discrete time Fourier transform, Z transform, all of that we are going to refer to this base case. So let us try to find the inverse Fourier transform of this. In other words, show from definitions that okay, inverse Fourier transform of 1 over a plus j omega is indeed this. So forward case is trivial. Yes.
है की जर झोपलो तर
Okay, if you don't have a question, please mute yourself. Okay. All right, so the forward direction is trivial. your signal is this. So let's apply the definition of Fourier transform. Xt is e to the power minus at, a positive. Since we have a UTC.
Sir, your screen is lagging
Yes.
a bit.
The screen is not shared.
Sir, your screen lagging.
Sorry?
Lagging.
It is lagging.
Yes, sir.
Okay. So is this okay now?
So we're not able to see the PDF that you were sharing before.
Okay. Let me stop sharing and again I will share.
And also, sir, your voice becomes stretched because of your network connection, I think.
Yeah, so maybe there is some connection issue. Let me share again now. Let me check the connection first. So is this okay? Can you see my screen?
Yes, sir.
Oh.
Sir, you're not audible here.
Hello. Am I audible?
Yes, sir.
Yeah. Okay. All right. So I hope this is fine. Yeah. Integral from 0 to infinity, and then you just take integration of this, which turns out to be this. Okay. This vanishes at infinity because a is positive. Yeah. And you just evaluate this integral at 0, and it turns out. So that part you already know. So let us find the inverse Fourier transform of this from the definition. Okay. So we are multiplying numerator and denominator by this complex number a minus j omega. So denominator becomes like this, and yeah, everything else should be straightforward. So we are just using this definition to get back xt. Okay. So let's expand this, expanding this complex exponential, and yeah, multiplying the two complex numbers. So this will be a times cos omega t and all that. Yeah, so you can verify that you indeed get this quantity. And since this is over minus infinity to plus infinity, we can just throw away odd functions. So this, for example, is an odd function. So we can throw this out. Yeah, this one. This is also an odd function, so we can throw this out also. Okay, so both purely imaginary components are odd functions, so their integral will be 0. So they are thrown out, and you are just left with these even functions. Okay, a cos omega t and omega sine omega t. So let's cancel this 1 over 2 factor and integrate from 0 to infinity. Okay, since these are even functions. So up to this, everything should be fine. And to simplify this, we are going to use some standard integrals. Okay, so I've put it up here. You can refer to this list of definite integrals from Wikipedia. Okay, so this is the one we will refer to, these two basically, yeah, where I'm pointing by the cursor. Okay. So let's look at this quantity first. A cos omega t plus over a squared plus omega squared. Let's do it first for t greater than or equal to 0, and then we'll do it for t less than or equal to 0. So let's suppose t is greater than or equal to 0. Okay, so let's identify t in this expression. So T in this expression is M. Okay. So M of Wikipedia is our T. Their X is our omega. Yeah. And their A is our A. Okay. So omega for us is X for them and T is M. So what they have given as this standard form of this integral is pi over 2a times this exponential. So we will get e to the power minus at. Okay, this thing will be as it is. Okay, so pi over 2. Let me check again. Yeah, pi over 2a, but we have an a here which will get cancelled with the a in the denominator. And there is 1 over pi outside the integral, so that is also there. So this term I hope is fine. You can check it later on. The second term also follows just by keeping track of symbols. Okay. So since this is for t greater than or equal to 0, yeah, so pi over 2, pi over 2. So pi will cancel, and yeah, you will just get e to the power minus at for t greater than or equal to 0. I think there was some comment. Yeah, screen is lagging, but yeah, hopefully you will get the recording also. Yeah, so that is the case for t greater than or equal to 0. So if you evaluate this integral for t greater than or equal to 0, you get e to the power minus at. So that part is there. Now let us do for t less than equal, strictly less than 0. Okay. So let's do this substitution. Tau is equal to minus t in this expression. Yeah. And if you do that simplification, you will get a negative sign here because sign of minus something is minus of sign. Yeah. For t less than 0, you get a negative sign here, and things cancel out. Okay. So this integral turns out to be 0 for t less than 0, and it is e to the power minus at for t greater than or equal to 0. That's why it is e to the power minus at times ut. Okay. So yeah, go through this again later on if you feel like it. We will refer to this when we look at inverse Laplace transforms.
So this is in the files section, right? So on Teams.
Yes. So notes in file sections, yeah, you will find this problem set is also there in file section. So maybe I can show it here. Yeah. Okay, it is not showing right now. Yeah, here it is. In class material, you will find this. Yeah, notes and problem sets. And you can also check out these links later on if required. So
your
get
screen is
into
not
that.
visible.
Okay, so it seems there is some lag. Okay, so hope it is visible now. If the problem persists, then tomorrow I will take class from my Linux machine. So there is a voice issue there, but yeah, this lag problem will not be there. So yeah, let us see how today's class goes, and tomorrow's class, yeah, there will be voice. My voice will be low, but yes, these lag issues won't be there. So. Okay, is the screen visible now?
No, sir.
Okay, still no. Okay, how about now?
No, sir.
Oh,
Yes, sir. It is.
Yes, now it's showing.
sorry.
Now it's visible.
Yeah, it's visible, right? Okay. Okay. All right. So that was inverse Fourier transform of complex exponential. Okay. So Dirac delta, hopefully you have already seen. So just plug in delta and you should get this. Okay, xj omega is equal to 1 from definition. So I assume you have already seen this. Yeah. So, yeah, if you put delta here, the integral will just evaluate to 1. Because you are evaluating complex exponential at t is equal to 0, which is 1. Okay. So rect function, have you seen rect function? Fourier transform of rect is sinc. If you have already seen this, then I will not go through this again. But if you have not, maybe quickly I can go through. So rect function is 1 for this interval t growing from minus t1 to plus t1. So maybe I will show it here. So this is my rect function. Sorry. Yeah. So when you take Fourier transforms, the limits are from minus t1 to plus t1, and the function is 1 over this interval. Okay. And now if you evaluate this integral, this is what you get, and yeah, this simplifies to this expression, and sine omega over omega. This is what is called a sinc function, and you need to do some more manipulations in here. Okay, so multiply and divide by w and things like that, which yeah, I'll leave that to you. So not w. So here you will multiply numerator and denominator by t1. Okay, capital T1. So 2 times capital T1 will be the magnitude of your sinc function. Yeah, at omega is equal to 0. And it looks something like this. So you get decaying exponential, not exponentials, sinusoids. So this is symmetric, and yeah. So this is sinc, and this is rect. Okay. So going from here to here is easy. Showing that Fourier transform of rect function is sinc function is easy. Showing the other way around is not easy from first principles. Okay. So this we will see perhaps tomorrow or on Friday. So this is also can be treated as an exercise. Yeah. So find the inverse Fourier transform of sinc function. Okay. So another important thing is integrability. Okay. So sorry. So integrable functions. What do I mean by that is yeah, this x is said to be integrable if this is less than infinity. Going from minus infinity to plus infinity. Yeah, if your function satisfies this property, then we say that the function is integrable, or yeah, if I use some jargon, it is called L1 function, but let me not use that jargon. Okay, for square integrability, you need the square of this function to be integrable. Okay, so this is square integrability. So to take Fourier transforms, yes, we ideally want our function to be integrable and square integrable. Okay, if your function is not integrable, then yes, formally taking its Fourier transform does not make sense. Okay, so for example, yeah, something like this function which is 1 over the entire real line. So this is a constant function which is 1 everywhere. This is not integrable or square integrable. So yeah, in speaking in strict sense, taking its Fourier transform does not make sense because the function is not integrable. Okay, so we have to somehow get around this non-integrability. So the way to do it is by taking limits. Okay, so what you can do is yeah, you can chop it up to finite windows like that. So minus omega to plus omega, or w, let me say, right? So if you take 1 over minus w to plus w, w is finite, this will always be integrable. And then you let w go to infinity. Okay, so it may not work in all cases, but it works in some cases. Okay, so the functions which are not square integrable, taking their Fourier transform or inverse Fourier transform does not make sense yeah, formally. So for such functions, you define their Fourier transforms or inverse Fourier transform in the limit like this. Okay, so that is what I have written here. So this x hat stands for sort of approximate or in the limit. So 1 over 2 pi, yeah, that is our factor in inverse Fourier transform. All of this is kept as it is. Only thing which is different is we are taking w and minus w instead of infinity and minus infinity. And then we are letting w go to infinity. Okay, so the functions which are not square integrable, we are going to use this trick to find their inverse Fourier transforms. Okay, so that will allow us to find Fourier transforms or inverse Fourier transforms of functions like this. And you can show that this x hat and the original x which you started with. So x j omega was the Fourier transform of this function x. And while taking inverse Fourier transform, you found it like this because x j omega was not square integrable. Okay, so if x is quote unquote nice, so what do I mean by nice is it satisfies some Dirichlet conditions. So continuous, finite discontinuities and things like that. Then these two functions are almost identical. So the inverse Fourier transform, what you obtain is exactly same as the function you started with, except perhaps yeah, few points. So those technicalities let me not get into, but yes, this thing I hope is fine. Why you need something like this? Let us take this example so that we understand how this is done. So let's take Fourier transform of or inverse Fourier transform of 1. Okay, so we have seen that Fourier transform of Dirac delta is 1, and now we want to find inverse Fourier transform of 1. So let's do that in the limit because 1 is not square integrable. Okay, so we are taking this finite w and then we are letting w go to infinity. So this integral we had seen in the rect function. Yeah, so this is just a Fourier transform of rect function, which turns out to be the sinc function. And then we are letting this capital W go to infinity. Okay. So you can do some substitutions in here, and in the limit you can show that this approaches Dirac delta. So the way that is done informally is as follows. So W is basically this width or 1 over W, and yeah, as W goes to infinity, this goes narrower and narrower, and as W goes to infinity, this sinc function approximates converges to the Dirac delta function. Yeah. So you can show that you indeed get the Dirac delta function as the inverse Fourier transform of the constant function.
So
Yes.
So any function, so can we say if we compress it infinitely, it becomes the delta function? Because then the shape does not matter.
No. Okay, so idea behind the Dirac delta is as follows. You keep the area under the curve constant. Okay, so if you take some function, okay, any function. So for example, Gaussian or a triangle or a rectangle, or yeah, any weird function like sinc or whatever. So the area, so okay, so if the width is this width is a, then height must be 1 over a. Okay. So if this is a, then this is 1 over a, like that. So similarly, you keep the area under the curve constant. So if you compress it in that manner, then okay, you can show that in the limit it approaches Dirac delta. So if you preserve the area, then yeah, any arbitrary function, then you can compress it. So its height, you make it infinity as the width shrinks to 0. So in that sense, yes, you can take any function, and if the area under the curve remains fixed as 1, then okay, in the limit as the breadth shrinks to 0 and height goes to infinity, it approaches Dirac delta. Does that make sense?
Yes.
Okay. All right, so we are almost out of time, but yeah, let me see. I want to say something else. Maybe a couple of minutes I will take. So I hope that is clear how the Dirac delta and 1 form a Fourier pair. So 1 and delta. I should have written it the other way around, but anyway. So Fourier transform of Dirac delta is 1 and its inverse Fourier transform is Dirac delta. And if you take 1 here in time domain, then you can check that you get 2 pi times delta omega in here. Omega. So you can start from this first and take its inverse Fourier transform. So 1 over 2 pi will cancel this factor while taking inverse Fourier transform, and you will get 1 here. And going forward, you can use these limits idea like this. Okay. All right. So times it is taken for granted. Yeah. I mean, you just show that the Fourier transform of Dirac delta is 1 and they form a Fourier pair. But yeah, the reason I'm doing this is, yeah, it's okay. In the first course, you can take it for granted directly. But yeah, ideally, you should justify why the inverse relation also holds. And once you know that, then you can use it directly. So for example, here, now once you know that complex exponential and this, they form a Fourier pair. Now, if you want to find inverse Fourier transform of any rational function, you can just use partial fractions and okay, excuse me. Now you have seen or you have verified that, okay, this is indeed the inverse Fourier transform. So yeah, just use partial fractions and use the formula directly. Okay, but what I'm saying is just showing that the Fourier transform of this is this does not automatically imply the inverse Fourier transform of this must be this. Okay, you need to justify this. So yeah, either you can show from first principles here that okay, this you can derive this from this, or you can proceed like what we have discussed. Okay, so those are technicalities, but anyway, I thought you should be aware of these things. So it's 1:02. Let me just take 2 minutes. I will quickly define the Fourier transform of sine function, and then tomorrow we can proceed from unit step and Fourier transform properties. Okay, so the sine function looks like this. So sine of something is yeah. If the okay, so if t is positive, so let me call this t. This is axis t. If t is positive, then sine of t is 1, and if t is negative, then sine of t is -1. Okay, so there is some comment. Yeah, please don't do this. Okay, if someone is purposely removing someone, then yeah, this is not good. Okay, so this is what we mean by sine of a function. Yeah, so SIGN. So sine of t is 1 if t is greater than 0, and it is -1 if t is less than 0. At 0, it is just 0. So there is a discontinuity here. Again, you can see that this is not square integrable. Yeah. So square of this is 1, square of this is 1, and yeah, if you integrate 1 over the entire real line, it's not a finite integral. So we run into difficulties while defining Fourier transform of this because the function is not square integrable. So we are going to use the trick of limits which we have seen before. So let's consider first this function. Okay, so let me draw this. It will be easier to see it like that. So yeah, this looks like this. E to the power -at ut for t greater than 0, and e to the power at u of minus t for I mean, yeah, x of t is like this. Okay, so u of t keeps these terms. So this is a decaying exponential, and e to the power at for yeah, u of minus t is only non-zero for negative values of t. So when t is negative, yeah, this is a decaying exponential. Yeah. And as we take the limit as a goes to 0, this this xt approximates the sine function. Yeah. So these decaying exponentials as a goes to 0 will approximate the signum function. Let me see if there are any questions. Okay, no. Yeah. So hope this is fine. Yeah. Taking a strictly greater than 0, and later on we are going to take limit as a goes to 0. So hope everyone sees that as a goes to 0, xt converges to sine function. Okay. All right. So let's find the Fourier transform of this first. So this we already know, 1 over a plus j omega. This also we know, 1 over a minus j omega, and this is the Fourier transform of this function. Okay. And now, as I said, you take the limit. as a goes to 0. So in the limit, this term will go to 0, and yeah, you are left with 2 over j omega. Okay, so the Fourier transform of the sinc function defined like that in the limit is 2 over j omega. Okay, and you can do the other way around also, just using the same idea. Inverse Fourier transform of this, you can show that it is the signum function, but we don't need that. We just need that the Fourier transform of this sine function is 2 over j omega, and we will use this to define Fourier transform of ut. So yeah, you can go through this, and we will, if required, we will again derive this tomorrow. Okay, so I'm already out of time. Let me stop with that. I'm here if there are any questions. Those who want to leave can leave. I will stay for a couple of minutes in case there are any questions. Otherwise, yeah, the lecture is done. So thank you all for attending.
Thank you, sir. Sir, here, why didn't we just take ut minus u minus t? Why did we take e power minus at, then we approximated 820?
Yeah. So the way I have started, I have not obtained Fourier transform of unit step from first principles. So by first principles, I mean from definition. Okay, so I'm assuming we have not derived the Fourier transform of ut. This is more difficult to derive from first principles directly. So that's why I started with complex exponentials. Then I'm defining this Fourier transform of sine function, and I will use this to derive Fourier transform of unit step. So yes, you can proceed
Okay,
like
sir,
that. Yeah, but in that case, yeah, you need to. Yeah, sure.
Thank you, sir.
Yeah. Any other questions? I'm still here for a couple of more minutes if there are questions. Okay, so perhaps not. So, okay, thanks again, and see you tomorrow then.